All right, you're on.
All right, welcome everyone. We are going to aggressively attack sort of a difficult topic. So acid-base physiology, but that is like our bread and butter, mostly the acidosis part of it. So you see like equations and stuff up here. This is just sort of like drive home some points that hopefully I'll make in an understandable way. But we'll just start out of the gate and try to make this as simple as possible and give you guys a framework with which to look at acid-base disorders. Sort of a stepping stone to maybe read about it more and learn more about it. So, acid-base, we'll start off here on the right hand, I guess left hand side for you all. And acidosis or acidemia, acid in the blood, is defined as a pH of less than 7.4. So 7.4 is like where we want to be. When you guys see those blood gases that come back at like pH of 7.1, pH 7.2, you understand that that means acidosis, correct? Of some nature. All right? Anybody lost with that? Okay, good. So now, how do we determine what's driving the acidosis, or what type of acidosis is it? So this is the equation to think about. So H plus, think of acid, okay? Your concentration of hydrogen, think acid. What's an acid that a lot of people are like familiar with? Hydrochloric acid, right? HCl. H plus, Cl minus. So the H plus part, acid, okay? So think of H plus concentration as the degree of acid, and that is equal to the ratio of your PCO2. So the PCO2 in your blood, we breathe off PCO2. PCO2 is a metabolic byproduct. It's part of this buffering system we'll get into. But we need to breathe off PCO2. Anybody lost there? No? Okay, good. Over the bicarbonate level in our blood, okay? Bicarbonate also involved in cellular buffering system, all this stuff. But that is what we see on our BMP, right? We have a bicarbonate on all of our BMPs, all right? So this, you need to get a blood gas, ABG or VBG, to see your PCO2 and your pH. And then you get that on your ABG, VBG2, or you can see it on your BMP, okay? So the degree of acidosis is related to your PCO2 over your bicarb. Knowing that more H plus equals more acidosis, what in my equation will drive that H plus up?
Either the numerator or the denominator. Good job, the number.
Perfect. So let's start with the numerator. So what happening in the numerator will drive an increase in H plus in the blood, or acidosis?
Increase.
Yeah, absolutely. Increase in PCO2. Do you know what we call that? A high PCO2 acidosis, basically. Hypercarbia, but it's a respiratory acidosis, okay? Have I lost anyone? Does that make sense? Okay. So what are the ways we can retain PCO2? Well, lung and airways. What's a big one we see a lot? A lot of people smokers, or they've got asthma. So COPD, asthma, bronchospasm. Basically, the airways are bronchospasming. They can breathe in, but they can't breathe out that PCO2, so they retain it in their blood, and they get an acidosis, okay? Because we know, in this formula, if our PCO2 goes up, that's going to drive our acid up, okay? So COPD, asthma, you've got a big bump in pneumonia. Sure, that we'll leave that there. Central CNS causes. So here I'm thinking of things that will make you hypoventilate or not breathe enough to get off your CO2, so you retain CO2. So what's a med we give a lot that reduces the ability to breathe? That causes us to hypoventilate potentially, suppresses our respiratory drive. Narcotics, yeah, perfect. So iatrogenia, narcotics. We do it to them, okay? And then you can have other things like obstructive sleep apnea, obesity hypoventilation syndrome. You're just not breathing, you're not ventilating as well, you're not breathing as much. You can have a CNS tumor or stroke to your respiratory centers that causes them not function as well and hypoventilate. Does that make sense? So you can have something intrinsic to the lungs or the airways, COPD, asthma, pneumonia, fusion, whatever. Central, meaning your brain's not telling the body to breathe as much as it should and blow off this CO2. Or you can have like chest wall things, like restrictive issues around the chest wall. So like restrictive lung disease, people with like kyphoscoliosis, it's harder for them to take big deep breaths. Burn patients, the eschars, they can't expand their chest wall as much to breathe and then breathe off that CO2. So does that all make sense? So think of the things that can cause us to retain CO2, not ventilate enough, not breathe off your CO2, and then just go back to your equation. Okay, what's going to increase H plus in my blood? It's one of these two things. If our PCO2 goes up, our H plus goes up. Okay? Everybody tracking? Does that make sense? All right. The next part of this is a lot. I mean, we see this a lot in the ICU. Our respiratory failure patients, our COPD exacerbations, our asthma exacerbations. People need BiPAP. We put that on to help them ventilate, help them breathe. But another big one we see is what's the other part of this equation that can go awry to cause an increase in H plus? What about, let's go to the denominator now. We're talking about bicarbonate. So what do we see people with an acidosis, DKA or sepsis, where their lactate's high, and what's their bicarb? Is it usually normal or is it usually low? Right? It's low, right? So if we reduce the denominator, right, this is going to increase, right? It's just math. Okay. So decrease bicarbonate. And there's sort of two flavors of this that we'll get into. And I kind of thought about getting into this, and I said, okay, let's just get into it because you hear these terms all the time. Okay? So this first one is called an anion gap metabolic acidosis, where your bicarb goes low. Does that sound familiar to anyone? Okay, good. So this is where we're going to get a little bit like esoteric and go into the clouds, okay? You can take this in, or you can forget it, watch it again. But an anion gap metabolic acidosis, I'm about to do some yoga, but the body loves electroneutrality. It wants the same amount of pluses as the same amount of minuses in the body. It's just like very zen, okay? And so when it gets unzen, things get screwed up. And it will do everything it can to maintain the same amount of positives and the same amount of negatives. We call those cations and anions. So the big ones in the body, the big cations in our BMP model here are sodium. That's pretty much the main one. Sodium. And then our cations, our negatively charged ions, are bicarbonate, and chloride. So when we look to calculate our anion gap, we do sodium minus your chloride plus bicarbonate. Okay? And if we were to do that up here, it would be 135 minus your chloride is 100 plus 25. So 135 minus 125 equals 10. Okay? Normal anion gap is 10 to 12. So that's normal. Okay? So here's my little model just depicting this. You have your concentration of sodium, you have your concentration of bicarbonate and chloride, and then these are the leftover negative things like phosphates in there, your albumins in there. Those are the other like negatively charged things that make up the anion gap. But same amount of positives, same amount of negatives. Okay, so what happens when we add another acid to the mix? Our big one we see is like lactate, another negative charge, okay? So you're adding an acid, this is an acid, it dissociates to these, and then an anion, okay? So this is acid. What does the body like to do with acid? It likes to bind it up with bicarb and shuttle it over here to CO2 so we then breathe it off, okay? So if that happens, what's going to happen to our bicarbonate as this guy combines with this guy and goes over here? Your bicarbonate's going to decrease, right? So it shrinks, and then your anion gets added to the anion gap pot, and it increases your anion gap, okay? It's all to maintain electroneutrality, the feng shui, the same amount of positives and negatives. Where am I at? 50-50 on losing, maintaining? Okay.
Good.
Watch it again.
Hanging on. You got this?
Yeah, yeah. And I'm not a chemist, like, so someone might technically watch this and be like, it's not quite right. But like, this is the way I think of it in my head, and it seems to work out most of the time. Okay, so this is what we're talking about, contributing to that anion gap metabolic acidosis. So what are those things? Gold mark, okay? Oh. Glycols. Ingestions, so this is like ethylene, propylene. Anybody hear? Oxyproline is a metabolite of basically Tylenol, so like a Tylenol overdose. That'll give you the anion gap metabolic acidosis. L-lactate, we're pretty used to that one, right? That's our big one we see here. D-lactate. So this happens when you have small bowel overgrowth, usually like bowel procedures, or you get a certain amount of bacteria in the small bowel, which then takes carbohydrates and makes D-lactate and can give you an anion gap metabolic acidosis. Not common, not something we'll see, but that's just the mechanism of that. This is methanol ingestion. Here's aspirin. Renal failure. Kidneys can't control kind of like your acid-base status. And then ketoacidosis. So like DKA, alcoholic ketoacidosis. You make, so like DKA, beta-hydroxybutyrate is like your acid that we can, and acetoacetic acid that we can test and find in your blood when you're in DKA. So that's what's contributing to that, okay? So that's what we mean when we say an anion gap. Cool? Make sense?
Alcohol ketoacidosis?
Yeah.
Is that like ethanol, like?
Yeah, yeah. And then you can also get like starvation ketosis. Cool. That's probably the most complicated part of this. but to just understand that that's what's going on to create your anion gap. All right. Oop, this one's metabolic. Respiratory acidosis, decreased bicarb, metabolic acidosis. Just think of your equation. Okay? All right. Now, have you heard of NAGMA? So NAGMA is a non-anion gap metabolic acidosis. So basically what you have here is you don't have an anion gap. You have a normal anion gap, but you still have a low bicarb. And typically what happens is the kidneys compensate by increasing the chloride component. So we also call this a hyperchloremic metabolic acidosis. Okay? They want to keep the same amount of negative charges, okay? So the bicarb goes down, the anion gap stays normal, so what has to increase? The chloride has to increase in order to maintain the same amount of negative charges and the same amount of positive charges. And things that will do that, the mnemonic is Durham, so diarrhea. Basically, you lose bicarb through your GI tract, and then your kidneys adapt by increasing your chloride retention, so you maintain a normal anion gap, but your bicarb is still low because your chloride comes back up.
Would you have a high serum chloride level with all of this?
Yeah, you typically, that's why we call it a hyperchloremic metabolic acidosis. Also, this one's ureteral diversion. It's kind of weird. This is a weird procedure. You don't need to remember it. It's basically where you like hook urine up the bowel. People with like cancer, and then they pee out of their bowel, and that creates all sorts of like metabolic disturbances and non-iron gap metabolic acidosis. RTAs, renal tubular acidoses. This has to do with the kidneys' control of bicarbonate, so they can't control the bicarbonate as well, and you either don't retain it or you waste it. So your bicarb goes low, but it compensates by, again, increasing the chloride. This is hyperalimentation, which is like TPN. TPN has a very high chloride load, so it will increase the chloride, and by default, to maintain electroneutrality, the bicarb will go down. And then this is Addison's disease. I'm not going to go into that. And then this is like, there's some other miscellaneous weird ones, which you don't need to worry about. And I would also add here is the big one that we do to them is like normal saline. Lots of normal saline has a high chloride content and a lower pH. And then also if you give like a lot of anything like or half normal saline or like D5W, all those things will do it too. I remember when we were always pushing normal saline and keeping people on maintenance fluids in like the neuro ICU, or pushing a lot of hypertonic saline, or had people on these solutions, they would almost inevitably always have a non-gap acidosis or a NAGMA. Okay. This is kind of where we live, like in the ICU. This isn't like as interesting, but basically to know that a pH greater than 7.4 is alkalemia, or alkaline blood, basic blood. So your base part of the equation. Same rules apply, except here your acid content gets lower. So, okay, how is the H plus going to get lower from a PCO2 standpoint?
Breathing out too much.
Yeah, so decreased PCO2, and this is a respiratory alkalosis, okay? So, things that can make you hyperventilate, basically, there's multiple things, but if you have a PE, you're going to overbreathe to overcome that, get to Kipnick. Restrictive lung disease, pneumonia, at least initially, maybe before you get acidotic, you'll overbreathe, trying to compensate and breathe yourself down to respiratory alkalosis. Sometimes people with sepsis are tachypnic and get a little bit of an alkalosis before like the acidosis sets in. That's under kind of like systemic causes. There's other CNS things, same things that apply here, not OSA, OHS, but CNS, stroke, tumor. Pregnancy, basically increased progesterone basically drives people to hyperventilate, and pregnant women should be alkalotic and have a respiratory alkalosis. Let's see. Pain, anxiety, liver failure, hyperthyroid. Those are other like systemic things that can cause us to breathe faster and deeper and breathe down our CO2, breathe it off more. Does that all make sense? Cool. Okay. And then what else will decrease? So we talked about the numerator. What else? What will if our bicarb goes in what direction will it make this go lower? We divide by a higher number, yeah, so increase HCO2, 3, or increase bicarb, and this is metabolic alkalosis. Not going to really like go into that as much. Basically you either are administered or ingest like a more alkalotic solution, and then the kidneys in sort of a maladaptive fashion can like feed forward and sort of continue on the metabolic alkalosis component of that until you intervene with different interventions, which I won't go into. But this isn't like something we really ever see, at least in the ICU realm, typically. So not as interesting, but to understand that this is that component, that increasing. Okay. Now, I talked about like pure things happening, but let me just give you an example. You can have multiple, up to like 2 or 3 of these things all going on at the same time. So when we write a blood gas, say 7.2, and then, so this is pH, and then I always write it like this, the CO2, and then this is the O2 concentration in the blood, and then this is the bicarb. So we write it like that. So say the CO2's 40, this is 100, you don't really need to worry about that as much, but then this is like, we'll say 10, right? What's a normal CO2 in the blood? Yeah, it's like 40. What's a normal bicarbonate? What's it?
24.
Yeah, like 20, 23, 24, somewhere around there. Okay, so let's talk through this real quick. What's our pH? Is it greater than 7.4 or less than 7.4? Okay, it's less than 7.4. So we're in what side of this thing? Acidemia. Okay. And then so then we go down to our what's the issue here? Do we have a PCO2 issue? We're acidotic, so we must have an increase in H+. And then where's the issue here in that equation that's driving the H+ issue? Good, both of them are contributing. Primarily the bicarbonate. So the bicarbonate's low, raising our H+, but we say 40 is normal, but it's not normal when you have a pH of 7.2. So what does this really So you have a metabolic acidosis and a respiratory acidosis as well. So this is typically what we run into in the ICU. So RTs, what do we need to do about this PCO2 of 40? We need to breathe it off. So we need to increase our respiratory rate, increase our tidal volume, increase our minute ventilation, essentially to breathe this down to try to meet our acidosis, while in the meantime we're trying to correct our bicarb issue. Maybe that's fluids, antibiotics if they're septic, source control, if they're bleeding, blood, whatever's going to increase this deficit of base here. Pressors. But in the meantime, we got to decrease our CO2. Because remember, when our acid is combining with this and this is coming out of solution, we're creating more of this. So we got to breathe it off. So that's where things come together in your acid-base disturbances. In this example, your metabolic acidosis and your respiratory acidosis. Do people get that this, though normal if this pH were 7.4, we need to breathe this down to improve our ratio here because our HCO3 is low, our bicarb is low. We have a metabolic acidosis and a concomitant respiratory acidosis because we have not breathed that down enough to create a ratio where this now is normal again. And as we breathe the CO2 down, then we'll start to see our pH increase 7.25, 7.3, 7.35.
So would you say that if the CO2 was on the more alkalic side, it would only be a metabolic acidosis then?
Yeah, and there's a way, and I won't get into it here, but there's a way to figure out, are you compensated? For your metabolic acidosis, are you compensated? Maybe that could be next week's talk. It's called Winter's formula. Okay. Little teaser. PCO2, I think this is right, is equal to 1.5 times your bicarb plus 8 plus or minus 2. I hope that's right. It's official now. I'm pretty sure that's right. So basically, if your PCO2 is equal to this within plus or minus 2, then you're considered compensated. So let's see. So in this example, 1.5 times 10 is 15, plus 8 is 23, plus or minus 2. So are we there? No. Right? This would need to be like in your 20s, 20, 25 range, 23, 25. What's up? Yeah, in order to, because it's all about the ratios, right? You went down here and you basically stayed what you would call with a normal pH, normal here, but it's not normal anymore, okay? We got to compensate and breathe it down. So that's why all these people that come in very acidotic and we put them on the vent, that vent is a tool to maintain our pH. People can't sit at 6.9 and expect them to survive. They're melting, so to speak. Does that make sense? So we got to work with our vent as much as possible to get their CO2 down to improve our ratios to where our pH now is normal, or at least above 7.25. Everything's a trade-off, right? Questions? We started 5 minutes late.
Yeah,
make us do it. Yeah.
I'll own that one.
Yeah, you didn't have anything ready.
Caught on camera.
I just wanted that on tape. In
That's a record show.
perpetuity. Cool. Any questions, concerns?